Swayam Prabha. Digital India. Educated India.
So, because I have put a second converter for facilitating the reversal, right? I will have to add the inductance and so on and so forth, add a firing angle which is actually 180 minus alpha 1. Because of which what happens actually is there is a circulating current. That circulating current is actually going to pass through the inductance through this back to the three-phase mains. Right? That circulating current is the inductance current alone. That is not anything to do with the load current. So, converter 1 supplies best part of the load power and a small amount of circulating current. Converter 2 essentially receives that circulating current. It doesn't receive the load current because the load current will go only within the load and converter 1. So, converter 2 will take that circulating current, feed it back to the mains. But you are not going to have much of losses because it is inductance, no power loss. There may be small resistance which will definitely have some amount of power loss, but much of inductance, it will not have any significant power loss. So, it will not tell on the efficiency so much for the converter and so on. Now, if I want the current to flow in the opposite direction. Yes? If the converter 2 is supplying power, how can you have the alpha greater than 90? You just cannot. If alpha is greater than 90, it can only do one job. It can take the power from the DC side and feed it. It cannot really supply the power. Right? Rectifier can supply the power from the AC side to DC side. Inverter can supply the power only from the DC side to the AC side, not otherwise. And currently I am drawing a lot of power from the AC side towards the load. So load is eating away everything, whatever it is doing, right? It is doing some work. So what is actually going as the circulating current is the small portion of the power, or you can say reactive power in this case probably, which is flowing back to kind of AC mains, nothing else, right? So this is clearly working as a rectifier and this is clearly working as a inverter, line commutated inverter. So whenever I am talking about dual converter, we will have dual roles for both of them. So you are going to have basically the converters, among the two converters, if one is working as a rectifier, mainly that is working as a source of power. The other one which is working as an inverter is only sitting there to take over the operation if I need some regeneration or something like that. So just to mention for continuity's sake, if this is alpha 60 and this is alpha 120, and instead of this load, if I now connect a DC motor drive, I just connect a DC motor drive, right? Imagine the same situation like what we said earlier, right? At alpha equal to 60, maybe this is 220 volts. So this will also be 220 volts, obviously, because only with the opposite sign, as simple as that. And maybe this is 210 volts back EMF, right? I want to bring down the speed. Fine. If I want to bring down the speed of this particular DC motor drive by doing braking, previously what I should have done is to reverse the direction of armature, make alpha originally what was 60, maybe I had to make it on the other side. It's a big task because suddenly I had to jump from some alpha less than 90 to some alpha greater than 90. It's not going to be easy. Whereas in this case, already there is one converter working with alpha greater than 90, right? And that converter is ready to carry the current and everything in whatever direction I want. There is no problem. It is connected in a very conducive manner. No problem at all, right? If I want actually now the current to flow from here to here, rather than flowing from the rectifier, which was flowing originally from the rectifier, it was flowing into the motor drive. Now I want it the other way around, because I want the machine to work as a generator and feed back the power, right? If I want the current to really flow in this particular direction, that means first of all I have to make sure that this voltage VD2 becomes less than whatever is my back EMF. My back EMF is 210 volts. Back EMF is 210 volts. That means my terminal voltage has to become less than 210 volts, which indicates that instead of alpha equal to 60 on the rectifier side, I might have to adopt 70 or 80 degrees. Correspondingly, I have to change the other side firing angle. Instead of 120 degrees, I have to bring it down to 110 or 100 degrees. Is that clear? If I do that, automatically I am going to reduce the VD2 value. Whether I like it or not, it will automatically come down. So, to bring the motor or bring the machine into regenerative mode, alpha 2 can be changed from 120 degrees to say 110 degrees. I am just saying 110 because I am assuming that 110, maybe I would have already gotten 200 volts or 205 volts. So now if I have only at 110 degrees, if I am going to have VD2 equal to say 200 volts, then what will happen? Automatically this current will start flowing from the machine into converter 2. Now converter 2 will take lion's share of the current. It is still working as an inverter, no doubt, but it is taking all the power that is being generated by the machine, transferring it over to the AC side, passing it on to the AC side. Now the rectifier is not supplying much power. It cannot also, because its voltage has now become 200 volts. How can it supply current now? It is not possible. So what happens is the rectifier literally is a mute spectator, quiet spectator. The other one is now taking over the operation completely by adjusting the firing angle. It has essentially taken over all the power that was actually saved in the form of kinetic energy in the machine. It is being converted into electricity by generator operation, and that is being fed through this to the three-phase mains. That is what is going to happen. Now as it feeds back, you are going to have less and less amount of, speed, because it is essentially, releasing its kinetic energy. So obviously the speed will come down. Once the speed comes down, you have to again adjust the firing angle as per your requirement. Here you didn't have to do any change of connection. All you needed was to shift the firing angle. Originally, which was 120, you have shifted it to 110. Eventually, you might shift it to 105, 100, 95, 90. That's it. Once you have come down to 90, you don't have any more margin left. That is the end of inverter operation. So dual converters, yeah, it is. That is true, but the motor inductance, again, you have to compare the armature time constant compared to the mechanical time constant. How much is the mechanical time constant? It will be in terms of at least seconds. Armature time constant, a few milliseconds. So compare the two time constant, you will realize that the reversal of armature current can take place much more quickly compared to the machine coming down to lower speed. Because machine will take a few seconds to show any significant change in the speed. Whereas the armature current can reverse quite quickly or change quite quickly within a matter of a few milliseconds, because armature circuit time constants are generally not large. That's the reason. Yes, the inductance you are externally putting can put a hindrance. I agree with that. So it is a double-edged sword. You can't eliminate it completely, but you have to choose it very carefully. It can't be too high, it can't be too low. That is what it is. Yes. No, only not alpha. When I am changing alpha 2 to 110, alpha 1 should have also changed to correspondingly 70. No doubt. Both would change. I will not change only one alpha at a time. If I do that, my DC link had it. I can't do that. I don't know whether I have answered your question. Was that your question? Tell me then. Why should you only play around with this? Why can't we do the change here and then get the entire thing going? That's what you are asking. That's what we did earlier. Now we have two converters. Why break our head with reversing the armature connection or reversing the field connection and so on? I wanted to eliminate that. That's why I put the second converter. Why put the second converter if you don't want to touch the second converter? You get my point. We are putting the second converter only to take advantage of that particular situation. So dual converter gives you the liberty to change over from one mode of the machine operation to the other mode of machine operation without really changing the connections, by just making small modifications in your control. So control, what you are making as modification is your firing angle control, nothing else. So that is the major advantage of using a dual converter. So normally dual converters are employed only in those applications where you expect frequent reversals and you also expect a significant amount of saving in energy because of regeneration. Because any industry will chuck us out if we are not able to justify the cost. If you are putting something costly, you better justify why you are putting it there. Right? What kind of savings you get by putting it. It's very important. Right? Is this clear? Okay. So we are now moving to the last topic. That is commutation overlap. The last topic on AC to DC conversion. All along we assumed that the sources are ideal. What we have considered as the AC source is ideal. There is no impedance, there is no resistance, transmission lines are all ideal. Excellent. If it is like that, the world is definitely not ideal. Right? So we are not going to have a source without some amount of inductance and resistance. We don't care much about resistance. Resistance is actually a less evil structure than inductance in one sense, because resistance will maximum dissipate power. It will not harm the current from getting transferred from one line to another. But inductance is not like that. It is very vicious. And you know, the conduction happens for longer than what it is supposed to happen normally. So if I have, let us say, 3 inductances along with the source. I am showing this inductance because it could be of transmission line, It could be a transformer leakage inductance, because I may have a transformer in my industry. When I have a factory, I may have an incoming transformer. What I get from the grid may be 11 kilovolts. What I require in my industry may be 415 volts. So I may have a step down transformer sitting in my incoming supply point, right? So this indicates essentially the leakage reactances of my transformer if I am talking about a factory. If I am talking about a big, traction kind of thing, it may be transmission line inductances. Now I have my converter. I'm showing, of course, one converter. There can be n number of converters like this connected, but I'm showing one converter connected here. And let's say it is connected to some kind of highly inductive load. Maybe a DC motor drive, maybe something else, whatever. So this is how it is connected. And let me take whether it is thyristor or diode, it does not matter at all in this case, but I am just taking thyristor so that everything will look uniform. That's it. So I have, let me again name this as this is VAN, VBN, VCN. Let me call this as LS, source inductance. Let me call this as LL, load inductance, and RL, which is the resistance of the load. Right? And of course, let's go by the same normal numbering. So this is 1, 3, 5, 4, 6, 2. Right? Okay. Let's say I am planning to fire this one at this point in time. Maybe alpha is 30, it doesn't matter. Whatever alpha, it doesn't matter. But it is uniform alpha for everything. Okay. Obviously, the current has to come from 5. Originally, 5 was conducting. And I am firing 1 now. So, 5 and 6 were conducting together. When I fire 1, 5 is supposed to give up instantaneously and 1 is supposed to take over instantaneously. That's what we were expecting, right? If 5 is conducting, the current would have gone somewhat like this. It would have gone like this, it would have gone like this, and it would have gone like this, and it would return through 6 like this through B. This is how it would have returned. This is the path for the current. When I fire 1, I will have the current actually going from here, right? And then it should go like this, it should go like this. All this is the same, no doubt. Load current, as far as load current is concerned, there is no problem at all. The load can carry the current directly because already it is carrying the current. The same current is going to be carried now by the load. Only thing is, it is going to be supplied by 1 instead of 5. That's all. It doesn't make a difference as far as the load is concerned. Whereas, for these devices, it makes a big difference. Originally, this LS was carrying full current, whatever is the load current. Let's say the load is highly inductive. Maybe it is carrying 10 ampere or 15 amperes of current. That 15 ampere is steadily flowing through this inductance. So this inductance is supposed to give up that 15 amperes of current in no time as soon as I fire device number 1, which is not going to happen because the inductance current cannot really go down to 0 from 15 amperes in no time. That's not possible. So the moment I consider that there is some source inductance, I cannot say that the current transfer would take place instantaneously from one phase to another phase or from one device to another device. So what will happen during that time? That is known as the commutation overlap interval. What we mean by commutation overlap is there is an overlap of conduction between the outgoing device and the incoming device. The incoming device is 1. The outgoing device is 5. Both of them are going to overlap with each other at least for a short while. How short a while, how long a while, that depends upon several factors which we are going to analyze a little bit. Right? So commutation overlap will come into picture only under a couple of situations. The major one is source inductance has to be there. If source inductance is not there, there is no question of commutation overlap. And the second one is the load current has to be continuous. The load current is not continuous, who cares? The source inductance would also have given up. Right? If there is no current, why should that inductance bother? It will bother only if it has stored some energy. If the current has already gone down to 0, it has given up. Right? So, only if the load current is continuous, I will have to worry about it. And the second thing is, the source inductance has to be present. And it has to be fairly significant. It has to be visible. Right? Its effect has to be felt. If it is microhenry or nanohenry, who cares? Right? So, it has to be significant. So, these are the two things which are very important if I have to observe commutation overlap. Right? So, let us try to first of all look at the normal waveforms what we drew earlier, if you may recall. If I am talking about a simple alpha equal to 0 degree condition, we normally said that I am going to have a waveform something like this. This is how the waveform is going to be. So this is how the VDC waveform will be, right? For alpha equal to 0. And I am going to have probably highly inductive load. So this is VDC. So if I am talking about a highly inductive load, I will have a current somewhat like this. It will be straight current. That's it. I should show like this. I have drawn very badly, but that is how it will be a straightforward current. If it is a highly inductive load, if I am talking about IDC or I load, if I call this as IDC, IDC will look like this. It will be a straightforward current, nothing more than that. And if I say that this corresponds to VAB, this corresponds to VAC, after this what will come? VBC, then VBA, then VCA, and then VCB. Right? This is how it will be normally. Right? This sequence you guys must have gotten used to now, hopefully. Right? 6, 1, 1, 2, 2, 3, 2, 3, 4, 4, 5, 5, 6. That's what I am writing in terms of voltages. So correspondingly, if I try to draw the current, right, I should have, whenever there is a phase conducting, I should have my current like this, positive current like this, right? And whenever I am going to have a phase negative conducting, I should have had the current going like this. So I should have the current going like this. So this is IA, this is again IA. So this is positive side, this is negative side. So this is what I can draw as the current. Right. But this is all well and good if I am talking about abrupt rise in the current. Please note, I have shown as though the current is having an abrupt rise. But that abrupt rise is not going to be possible if I am having some source inductance. At the same time, in fact, if I try to draw actually the current through device number 5, right? Device number 5 is conducting here. Are you getting my point? Device number 5 corresponds to this, CA and CB. Because wherever C is positive, that is device number 5 current. Right? So device number 5 current should have been somewhat like this. It should have started like this and then it should have gone like this. This is how it should have been. It should have again conducted abruptly and it should have ended abruptly after 120 degrees. And after 120 degrees, I fire one and one should start conducting. That's how it should be. But now, because of the commutation overlap, maybe I am going to have the current rising slowly. It will not really rise abruptly, but it will rise slowly, like what I have shown here. And similarly, when it has to fall, it is probably not going to fall abruptly, it is going to fall slowly. It is like an RL circuit, right? So it will essentially be exponentially increasing or exponentially falling. So same will be the case for 5 as well. So this will be falling slowly. This is how it will be. Now if I superpose this particular portion with this particular portion, because please understand, 5's falling current will coincide with 1's increasing current. You get my point? Both of them are happening simultaneously. When 5's current is falling, 1's current is increasing. So I should show it here as though 5's current is falling like this, when 1's current is increasing here. Around the same time, both of them are actually happening simultaneously. Right? So this is actually going to be the current of I5 and I1 respectively. So I am talking about I1 here, I5 here. Do you get this right? And the rate at which I5 is falling hopefully should be the rate at which I1 is rising. Both of them should be really in great synchronism. Otherwise, you will not really get the same amount of DC current all the time. Let's try to now draw the equivalent circuit of this converter only during the interval when 5 and 1 are overlapping with each other. So let me first of all take your help in drawing this. This is VA and this is